refer to you as Wave Boy. So you're. Oh wait, yeah. Did you get my follow-up email from yours? Yeah, you did really well. Have you had this before?
No, I just wanted to get it done quickly.
Yeah, but I know she didn't miss many. Good. All right, you guys ready for physics? That's the spirit. So let's see, start of a new week. Let's see what we got here. So your exam 3 retake is still open until tonight, as you hopefully know. We're starting chapter 19, waves. Let me do that. It's on the calendar, so you guys know, but this one's not quite as consecutive in the book. So chapter 19 is on waves in general, and then we'll start chapter 20 on sound. But then we're skipping and prioritizing. We'll skip from chapter 20 to chapter 26 on the light, because light can be treated as a wave. Has a lot of similar characteristics. So actually I'll probably start sneaking those in while I'm discussing waves. And when we get to chapter 26, it'll just be like, oh yeah. It just works for that also. So 19, 20, 26, then 27 on color, because I just love color. And then 29 on light waves. So that's all written down so when you get confused, but I don't want you, it's great to read all those chapters, but I know you guys have busy lives, so I don't want you to read a chapter thinking I'm going to test you on it when I'm not. So don't go consecutive there. For this week, we'll get through chapter 19, finish it next lecture. I'll start 20, but since I won't finish it, yeah, that's right. Just homework on chapter 19 will be due next Sunday. But that's all on WebAssign. If you don't know by now, then I don't know where you've been. So, okay, I like waves. One of my favorite topics in physics is the physics of music, and so I like this. My all-time favorite topic inside of physics and outside of physics is light. So I'm just going to be real excited this unit. So that's my disclaimer, and just forgive me now if I get kind of giddy. Oh yeah, and your superhero paper review is due by Wednesday. Yeah. It's painless checking in with me. You know, I'm just going to have you write down your name and the reviewer, and you both signed it, see the comments that it's worked, and you're checked off. You'll get points for that part of it. It's just you guys having to write a rough draft and get it reviewed. That's probably where you're stressing.
Do you need to hand in a physical copy of the...
Yep, as listed. Yeah, I need to, yeah. The easiest is, yeah, print off a copy. If you prefer, you can send it digitally if there's comments in there. Basically, I need to see that there's constructive comments. And I need to know that you didn't do it yourself, that someone else is vouching that, yeah, I reviewed this. Because, unfortunately, that's happened. Yeah, this was really good here. This stunk. They forward somebody else's name. Or, I don't know. Okay. So, chapter 19, vibrations and waves. Okay. We're going to start out with a demo in the dark. Let's try this one. Okay, so I have a UV laser pointer here, and I'm going to swing it. I'm going to vibrate it back and forth. And you can see the effect here. It vibrates. That's a vibration. I call that a wiggle in time. Because overall, it doesn't really go anywhere. It's just, but it is changing with time, back and forth. Back. That's a vibration. And the difference between that and a wave is that a wave is a wiggle in time and space. A wave will seem to move or displace itself. So let's see if I can do this. Glow-in-the-dark screen. It's a great toy I bought. So you can see it, I hope. Good. But if I move in space, whee, then you get what's called a sine wave, a sine curve. And that's usually how people represent waves. And if you're moving well, we just won't say that. I can, if I'm trying to move at a consistent speed here, you can see the vibration up and down, but it also displaces and moves over. And you guys are familiar with waves, like throwing a rock in water, in a pond, and you see the ripples move out, right? Think of a bobber setting in the water. You know, you're fishing. You're bored, though, because you don't catch any fish like me. So you throw a rock in. That's not going to help. But it makes a ripple, and you see the waves move out. That's like me moving. But the actual, when the waves go over the bobber, past the bobber, what do they make the bobber do? Go up and down. It doesn't like grab the bobber and whoosh it along like we think with a surfer. And so that might help you with a visual. The difference between a vibration, the bobber just bobs up and down, vibrates, wiggles in time, but the wave wiggles in time and space and moves across. Does that make sense? Since we're going to be doing waves for quite a while, conceptually, that's what I like to think. I'm doing it again. There-ish, okay. I love that. Anyway. UV laser pointer, $10 off of Amazon. It was great. So another concept here is mechanical wave, your book describes. Sound is a mechanical wave. That just means it needs a medium to be transmitted. This. You can see a wave propagate through the medium, the rods, or a slinky. You can make a pulse, and you can see it mechanically move something. Sound is like that. It moves the air. When you talk, you actually compress the air, and then it spreads back out, hits its neighbors, compresses them, and they spread back out, and you get a wave kind of like in the slinky. That's mechanical. The water waves I described, the water is actually moving. Those are mechanical waves. Whereas light is still a wave, but it doesn't need anything. It can be transmitted through space. We've already discussed this with the electromagnetic spectrum and radiant energy. But all those forms of electromagnetic radiation are just, you can think of them as like pure energy. They can radiate all on their own. They like drive themselves, whether it's infrared, ultraviolet, visible, gamma rays, X-rays, microwaves, radio waves. All those are forms of light. They just have different vibration rates, which we're going to call frequency. I'll get to that in a moment, but you've probably all heard frequency. So sound and light, they're both waves, water waves. How many of you have been to a sporting event and participated in the wave? You know, where you stand up and you whoosh. Think about that. We could do it, but you know, if you raise your arms and then it goes across. You can see individually you move up and down, kind of like the bobber. But the wave is going across and actually being displaced. So you can think of you as the vibration, wiggle in time, but you haven't moved anywhere. You haven't changed your location in space, so to speak. But the wave goes across the room. Now, you can result the source of all waves. Something has to be vibrating. You got to have something vibrating. This was swinging, right? I got it driven. You got to have something wiggling in order to get a wave. For water, you know, the rock can throw it in and splash it. For light, it's the electric and magnetic fields, which we'll discuss more later. They oscillate. They're naturally vibrating. So, and what causes that are the electrons in an atom. They're moving, and they can oscillate. And so there's still a source of something vibrating. With sound, right now, you can hear me. It's your vocal folds. They're vibrating. That's the source of my sound at the moment, anyway. But so the source of all waves is something vibrating. All right, let's do. You guys remember way back when you got a heavy object This is about a kilogram, and this is a fourth of that. Something heavy, something not so heavy, and you drop them. What do you know is going to happen? They fall down, and they fall at the same rate. So you expect them to hit together? You're right. That's still true with a pendulum and things that want to oscillate like this. So we can slow gravity down in a sense. Instead of going straight, you can put it on an inclined plane like this. And if I release them at the same time, what do you expect to happen? Will they get to the bottom together, or will one beat? Basically, they're not being pulled down. They're being pulled down straight, but the incline's in the way and redirecting them down the incline. So they're not going to accelerate as fast as 9.8 meters per second squared, something a lot slower. But they're still being accelerated down the incline. So they'll both increase their speed, but will it be at the same rate? You guys don't seem as confident. Why would it change? We just changed the direction. So here we go. Rolls off the... Fine, I'll just do this. This is not very level, is it? I'll give that a go. That's better. Until they run into each other. You get the idea. Now it's going too far the other way. My point is ideally they're the same. Oh, that was a good one. When they go straight. And it's the same reason. They're being accelerated down at the same rate. It's a smaller rate than g. It's a fraction of that, but it's still the same rate. So their mass doesn't matter is what I'm emphasizing here. So whether you drop it, slow it down, maybe we could have it somewhere in between. They'll go down faster, but they'll go down at the same rate. So with pendula, different pendulums, this one's heavy, it's made out of brass, and this one's rubber, it's lighter. So if you swing them, let's try my comb. We let go of them, and they're accelerated down, and the rate is the same. They're pulled and accelerated back to its equilibrium point, equilibrium position, at the same rate. So that means they end up swinging at the same rate. We say they have the same period. Period. That's the time it takes to go back and forth. So let's see, roughly go 1001, 1002, 1003, 1004. So we'd say the period is 2 seconds. So that's a term you're going to need to know. Period. We use it with the letter T for time. And that's just the time it takes for one cycle. Or vibration. We say it's swinging at a certain rate. How fast is it swinging? We say that in normal language. We don't mean velocity normally. We mean frequency. And that's the rate it vibrates. So these two are related easily. I think you can see, well, it looks like they're not exactly the same length, but close enough. Get to that in a moment. They takes 2 seconds to go back and forth. So for a rate, that's like how many cycles per second? How many vibrations per second? How would you relate that? If the period here is 2 seconds, how would you do its rate? That's right. In 1 second, it only goes half a cycle. So these two are related just like this. They're inversely proportional. Because when one gets bigger, the other gets smaller. And remember that. You'll need to do that to work a lot of your homework. But that's all there is to it. Just two ways to describe the same vibration. You can either talk about how long it takes, the time, or the frequency, the rate that it occurs at. Now, frequency is measured in cycles per second. And that happens enough, they give it a term, Hertz. And that's abbreviated as that. Hopefully you'll remember now with this little exercise. It's just how many cycles per second, you know, it goes back and forth one. Okay, there and back, there and back. That's one cycle. How long does that take? One cycle took 2 seconds. So it's a half a hertz. One cycle took 2 seconds. A half a hertz. I know, if some of you are sitting there going, okay, we get it. I've just learned that this gets confusing for lots of people, so I'm going slow. Half a hertz. What's your favorite radio station? Anybody? 94.1? Yeah. All right, and we're good physicists. We're good scientists. 94.1 what? FM. That's FM stands for frequency modulation. They modulate the frequency to get you the signal. Where AM modulates the amplitude modulation. But that's not a unit, so try again. 94.1 what? You guys, did you ever think about that? Very good. It's megahertz. You know, 1,000,000 hertz. So that means the frequency of that carrier wave for that station, that channel, is 94.1 megahertz. It vibrates 94.1 million times every second. That's a fast wave. Your phone, look up its frequency. A lot of them are often in gigahertz. That's even faster. But now maybe your microwave, you can look it up and see how fast those waves are vibrating. AM, do you know what range it's in? Say again? Nope, it's not gigahertz. Gigahertz would be faster. It actually goes the other way, so it's kilohertz. So it's not vibrating as fast as FM. And you need these bands, because if you're trying to transmit at the same frequency or around that, you're going to have interference. They can mess with each other. We'll talk about interference more too. But that's period and frequency. Now the neat thing with this is mass does not matter. The period and the frequency do not depend on the mass for a pendulum. We've seen that. Because what's accelerating them down is gravity. And we've learned that gravity accelerates all masses at the same rate. I just love reiterating this because we all learned that. While we're at it, because you will have a final. Which one feels a greater force due to gravity? The bigger one. Yeah. It has more mass, so remember Newton's second law? They have the same A, the same acceleration. And F equals ma. So they have the same A, sure. So they go at the same rate. But the bigger one is going to feel a bigger force. Well, think about it, yeah. And if it's bigger, it's going to take more force to accelerate it at the same rate as the smaller one. To get it going as fast, it's got more inertia. You got to pull harder. So here with pendula, just remember, mass doesn't matter. But something else does. And that is length. So start them together here. Yeah, well, I'll just be better. Okay. Long and short. They don't have to stay together. You'll see the point. I think you can clearly see. This one's oscillating more quickly. A lot more cycles per second. So its period would be not greater, shorter. And I do that because it gets confusing. It's time, but it's going more quickly. That means it takes less time to complete one cycle. So the period's less, smaller. But the frequency is greater. Yeah, it's going back and forth at a much higher rate. So those are proportional to length. And if we took these pendula to Jupiter, where gravity is greater, you know what would happen. You drop this on Earth, whoosh, it takes that long. If you increase G, what happens? It goes faster. I can't do that demo, sorry. So the period is proportional to length, and it's proportional to gravity. If we change gravity, that'll change how fast it swings. But it is not proportional to mass for a pendulum. Now, your book has an equation for you, and it is, the actual works out to be if you want to know exactly what it is sometime in your life, there you go. The period is 2 times pi times the square root of the length over gravity. And see the relationship here? We could have figured this out, that the L's on top and G is bigger. Actually, you already did. Think about it. If L's bigger, it goes more slowly. It takes more time to get back and forth because it can cover more distance, if you will. This one's shorter. Doesn't have as far to fall. So you increase L, you increase the time it takes to oscillate. But if you make it accelerate faster by going to Jupiter, we made it oscillate faster. So the period is smaller time. So if you want to add it in, to remember the period's proportional to the inverse of gravity, because if you increase that acceleration, the period gets quicker. That's why the G is on the bottom here. Again, a guide to thinking to help you remember this. Yeah? Oh, you're just stretching? Dancing in the wind. Woo-hoo. Okay. Now, not to confuse you, but to get some more definitions. A mass on a spring is a little different than a mass on a pendulum. We call this the equilibrium position. We call this the equilibrium position. We're trying to graph its position, if you will. So, let's just see here. We need a bunch of definitions for this wave stuff. Make sure we're all on the same wavelength. Okay, that's the equilibrium position. You think of it as 0. That's where it's happy. The forces are balanced. When you displace this, you just moved it away from the equilibrium position. And then a force pulls it back to restore it. I like thinking of it as a restoring force. But it has momentum. It's moving now. So it overshoots. But as soon as it overshoots, gravity's still trying to pull it back down, isn't it? So it slows down and comes back and overshoots. Slows down. It's just like throwing the ball up, right? You still have gravity the whole time. Remember that? What's G? And it's always down. It's constant. So it slows it down, stops it, and speeds it back up. It's always pointing down. In this case, we displace it by expanding the spring or compressing the spring, either pulling it down or that way. And it can start oscillating around that equilibrium position. It's always trying to be restored back to equilibrium. If you compress it, we've stored energy in the spring, and there's a spring force pushing it back to equilibrium. But it overshoots because it's got momentum. Now it's stretched, and there's energy stored in the spring again, and it tries to pull the mass back to equilibrium. It's got momentum, it overshoots. And you oscillate. You have a vibration. This one, just get in your head how fast it oscillates. Let's see here. 1, 2, 3. We can time the period and figure out the frequency, can't we? 1001, 1002, 1003, 1004. Okay, it's roughly a second. So the frequency is 1 hertz. 1 over 1, that one's easy. We're going to change the mass. It has a different equilibrium position. And let's see, what do you think? Will it be the same, faster, or slower? Got 1 vote for faster period. No other votes? 2 for faster. Let's just do it. 1001, 1002, 1003. Oh, it's faster than a second, isn't it? So, yeah, the frequency's faster. The period is smaller, shorter, more quick. However you want to think. T will be a smaller number. Why does it matter with a spring but not a pendulum? Now you can think of inertia. It's the spring trying to move the mass. It's a force pushing on a mass. And which one has more inertia? The big one. And so it resists that change in motion more for the same force. This pulls on it with a restoring force. But this one resists that change more. So it can't oscillate as quickly. Remember, with gravity, that's the same acceleration. This is the same force. This is the same acceleration. So they do move at the same rate. But remember, the forces are different. This force is bigger, lest you get confused. All right. When you pull it down, either one, you initially displace it. We call that amplitude. And as we saw with my UV light, you get a wave, a sine curve that looks like this. With time, the displacement changes like that. So if this were time, and this is position, it goes up and down and changes its position around the equilibrium position. How far up it goes is amplitude. That's the same as the distance it goes down on the other side, amplitude. Or for the pendulum, how far out it comes. Back. That's amplitude. When you guys listen to your stereo and you turn up the volume, you're changing the amplitude of the waves. You're not changing your radio station. You're not changing the frequency. You're not changing the frequency of the sound that comes out. You still hear the same song, the same notes. You're just making them louder. They displace more, which makes them move more air around. It doesn't make them move any faster, it just moves more around so it's louder. That's amplitude. You started this?
I was just wondering, is that the same with light as well? You change the amplitude?
Yeah.
It would change
The brightness/intensity. Color has to do with wavelength and frequency, we're going to learn. Just like infrared, red, orange, yellow, green, blue, violet, ultraviolet. They have different periods, different frequencies, different colors. But the amplitude has to do with its displacement. So ultraviolet has shorter waves. They vibrate more quickly. And infrared/red have longer waves that vibrate more slowly. But they could have the exact same amplitudes, how bright they look. Yeah?
So for sound waves, the amplitude is what determines how loud something is. What is the wavelength determine?
Well, so amplitude does determine the loud. Let's define wavelength first here. Wavelength is the distance one wave travels. It's the length of a wave. I love it when it makes sense. So let's look at this. Some of you are familiar with it. They use the Greek letter lambda. In WebAssign, it doesn't let me do that, so I'll probably most of the time in this class I'll use a W for wavelength. And that's just the distance one wave. You can represent that different. It's always the same length, but we call this where it's up, like a water wave. If the water's coming up, we call that a crest. So here's another crest. And another crest. And if the wave's down, Seems like it's dipping in. We call it a trough. There's another trough. So we have some names to call these bumps. So from crest to crest, that's one wavelength. That's the distance. Think if you're riding this wave, you know. You go from here, start at point A, and let's go to point B over here. Let's see. You think of this, the pendulum. You start displaced on the left side. You go back to equilibrium. Now you're displaced on the right side. You come back to equilibrium. Oop, now you're displaced on the left side. You're back to where you started. So you've had one cycle, one vibration, one wave. So that's the distance. You could also do trough to trough, from here to here. That's a wavelength. It's the same length. And for that matter, you can do any point. Let's say we start right here. When do we get back to that point? Here? No, because we're going in the other direction. Ah, here. So that distance is a wavelength. So that will change if it's vibrating faster or slower. That spacing is a gauge to tell you period and frequency. If you have a wave that looks like this, versus, I'll just do it on top of it. Was I consistent? Tried to be. You know, this one that's A and this one that's B. Which one has the shorter period? Period's the time it takes to oscillate back and forth once. This is time still. Yeah, B. It goes up and down. It's done a complete wave. In the amount of time wave A has only done half its vibration. Do you see that? So yeah, the period of B would be less than the period of A. Or we can say the frequency of B is greater than the frequency of A, because it's oscillating more quickly. And actually, the way I drew it, twice as fast. Half the period. And we can also say, how do the wavelengths compare between the two? Wavelength A is bigger than wavelength B. And by how much? Twice. Yeah. Good. A lot of definitions there. Here's something too. The amplitude. We had these together, displaced the same. Let's do it like half the distance, like this. We'll start like one has a bigger amplitude than the other. Do you see they have the same frequency though? Check them in the middle. There, there. They're going back and forth at the same rate. One is covering more displacement. Sorry, it's kind of hypnotic. Until they hit each other, got to start over. But amplitude doesn't affect the frequency. It's independent, for the most part. There's some technicalities we won't get into. But can you see that? So just by changing the amplitude, you don't affect the wavelength and frequency. All right, what have I forgotten to cover? Anything? Okay. This came up earlier. Any questions yet? Concerns? If you don't have this, you won't get the rest of this whole unit. All this definition stuff. It came up before. I said we'd get to it. Velocity equals what? Way back when with Newton, when force is in motion. How do you find velocity? Very good. Distance over time. Well, with a wave, we're looking at the whole wave in general. So what are we using for distance? a wavelength. What are we using for time? Period. There you go. Velocity is wavelength over time, or over period. But we can also write the period as what? Since the period's on the bottom there, you can see this is like 1 over t. Let me write it. This is like w times 1 over the period. And 1 over the period is the frequency. So this equation is what most people guide their thinking when they're thinking about the wave velocity of a wave. That was redundant, but so this is the wave velocity. And you need to differentiate wave velocity and frequency. People get confused. Frequency is the rate that it's vibrating. It's that vibration in time, the wiggle. But the wave speed could be different. A wave can transmit information or even energy. So like look at this rod here. This one right there. I can move it up and down at a certain frequency. But it produces waves that move in time and space. And the speed that this pulse seems to travel is what we're talking about for wave speed. You with me? You can make a pulse. Whoosh, and you see it travels over a distance. That's the wave speed. But it's related to the wavelength and frequency. And this is why with sound. If you wiggle something faster, the speed of sound in air, let's say, I'm talking. So I can talk high like this. We have a higher frequency. These waves would actually look smaller because it takes the same speed to travel to your ear. So I'm not changing this one when I talk. The air in the room can vibrate yay fast. I can't change that easily. We'll get to ways that it does change, but you're with me. So that's not changing. So if I vibrate the air more quickly, what has to happen to the wavelength? If this goes up, the wavelength goes down. I'm letting that sink in, my head and yours. So the size of the waves do what? If the wavelength goes down, wavelength is a smaller number now. Smaller. Wavelength is this distance. If it goes down, it's a shorter distance. Can you see the waves are going to look like they're shorter? So the idea is, I was trying to talk like B here compared to A. The wavelength gets smaller. The waves get shorter. It's vibrating more quickly. And that's kind of a key to music and sound. And if you, well, the reverse can be true. What if I make something with really big waves? The waves are really long now, long wavelengths, really big. If that number got bigger, then the frequency has to get smaller, which means it's not vibrating as quickly. That's a low note. There you go.
Is that speed always constant?
The speed of sound in a material is a constant, unless you change the material. Different materials have different rates that sound travels. Or if you adjust that material by stretching it, heating it up, temperature can affect the speed of sound too. But like right now in this room, there's nothing we can do to change how fast sound travels from me to you. Oh wait, I just changed it. Not the wave velocity. I changed the frequency, which means the wavelength had to change also. Or instead of talking like this, I can talk like this. It's the same frequency, but I've just increased what? The amplitude. So instead of talking like this, I'm talking like this. All right. Here's one. We'll see how well that turned out on the microphone later. Here's a little slinky. And it can rotate. I can turn it around and 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 around, and it doesn't go anywhere. So I put it on here, and then I start doing the same thing. I turn it, and look what happens. This is just to emphasize, I'm going up and down. I'm the source of vibration. I'm vibrating it up and down, or around and around. Here's one cycle. I start at the top, go around, one cycle, again, 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 again. I'm the vibration. But can you see the wave? If I turn clockwise like I was, say, watch this point right here. Keep your eye on that. If you haven't noticed it yet, keep your eye on that. I'm going clockwise. It appears to move, doesn't it? With a certain wave velocity. It's kind of an illusion because that individual coil stayed right there. The coil just goes round and round and round. That's the vibration. But the wave can seem to travel. And the distance here from crest to crest, that would be one wavelength for this one. And that corresponds to the time it takes me to go around once. 1001, 1002, 1003, 1004. You get the idea. I just wanted to show you in a different form. Any questions about that? Okay, there's two types of waves. Transverse and longitudinal. They're both in your book. Transverse and longitudinal. Transverse looks like this. That's what most people think about when they do waves. The reason it's called transverse is, think of an individual rod, or most of the things we've just done, the slinky on the overhead. This rod moves up and down as the vibration goes across. Up, down, up, down, up, down. But the wave, or the pulse, seems to travel side to side. They're perpendicular to each other, 90 degrees, transverse to each other. They're called transverse waves. That's why. Examples of transverse waves. Water waves. When you throw the rock in the water goes up and down, but the wave seems to go side to side. Transverse. Light is a transverse wave. We'll learn that it has an electric field that oscillates. It increases in this direction, comes back to equilibrium, gets displaced over here, larger, back to zero, positive, negative, positive. It's oscillating. There's a magnetic field also doing the same thing, perpendicular to that. Increasing, decreasing, positive, negative. So you got this thing going on. Anyway, John Travolta. Anyway, if you're doing that, but the wave, light, when they're oscillating, those electric and magnetic fields, the light or the wave is propagating sideways though, perpendicular to it. So, electric magnetic field, but I'm going perpendicular to it. Or electric field, going perpendicular to it. That's a transverse wave. The other kind of wave is longitudinal. And the difference is the vibration and the wave are in the same axis. They're along the same line. They're longitudinal. So like a slinky. If I compress the slinky, you can see the pulse, I hope, go back, go across. So the slinky is getting compressed and expanded sideways. But the wave is going sideways also. That's a longitudinal wave. You can do it faster. Increase the frequency. So you can still see the individual loops on the slinky are being compressed sideways. Same direction as the wave, longitudinal. Examples of that are sound. That's what the air is doing when I talk. Ah! And I'm making the sound go like this. It's moving sideways, back and forth, in the same direction it's traveling. Then it makes your what wiggle?
Ears or my drums?
Yeah, it goes in your ear canal, makes your eardrum wiggle. What's your eardrum connected to?
Brain.
Not yet. Good, the ossicles. The anvil, stirrup, and hammer, yeah. The little bones. So right on the other side of that membrane, they make those wiggle, and it transmits through those. Do you know what they hit next? Nope. Another membrane in your cochlea, and then it makes some fluid, like a ripple, go across through your cochlea. And as that ripple goes by, it's like they got bobbers sitting there, and they call them hair cells. And the wave ripple goes by, and it makes that wiggle. And that's connected to a cell, which changes something chemically, sends a signal to your brain. And that's how you hear. That's sound. But it starts out with a longitudinal wave to get to you in the first place. Sound needs a medium to travel through. It's a mechanical wave.
So in vacuum,
That's right. In a vacuum, there's no sound. So all those sci-fi movies in space where they have explosions and boom, and you can make a vibration. I can sit here and go like this all I want. But the only reason you hear this is because it's compressing the air, which then travels to your ear, and you hear it. If there's no air to get it or transmit it to your ear, you don't hear it. Here, Tommy. This is called a space phone. It's a toy. Hello! Shout away, Tommy. Say something. I like this because you can hear and see the waves. You can make transverse waves like this, right? You can make longitudinal because it's like a slinky. My favorite is, just flick it, Tommy. You can see it reflect back and forth. We're going to start talking about how waves can interfere. But it's connected to a diaphragm here, which couples it to the air. So this vibrational source makes the diaphragm wiggle like your eardrum. And then this couples it to the air, so it makes the air wiggle so we can hear it. I love it. Luke, I am your father. But anyway, it's called a space phone, and it's a toy. But one of my favorite toys.
sound waves can't travel in vacuum, but light can. 'Cause light.
Sound waves cannot travel in a vacuum.
sound
But
waves-
yeah, cannot. But light can, because it's pure energy. It drives itself. It travels through space. Here's a whip. Let's see how good I am today. Do, 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 do. Yeah. That's actually making a little sonic boom. That sound you hear is because the tip of this is traveling